Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about synthesis of glycosides, and among that synthesis of glycosides, one of the we are discussing the glycosylyl formation of a bond, means where there is a in a glycoside or glycosylyl donor acceptor concept that we are actually discussing. So remaining part of that we are continued today. Our discussion will be we are continuing right now. So what is that? The trichloroacetamidets, and as we know that trichloroacetamidate at an anomeric hydroxyl group, and it gives the very selective anomeric control of that selectivity at hydroxyl group OH, anomeric carbon atom, or we can refer as carbon number 1, but in some of the book we can refer as 2OH, means heterocyclic is always considered as 1 over here, but in some of the books they can refer as anomeric carbon atom, that hydroxyl group. As we know that it is present in the two form, one is alpha and another one is a beta, and as we know that alpha side means what? Above the plane, and beta side means what? Alpha side is below the plane, and beta form is that hydroxyl group, anomeric hydroxyl group are above the plane. So that you have to remember here. And why this trichloroacetamidets is essential? Because it is act as a donor, because for the formation of the glycosylyl bond it require the one acceptor donor, then and then reaction occur, and there is a formation of the new bond between that oxygen and the carbon atom. There is a elimination of, generally when that glycosylic bond is formed, there is a elimination of the water molecule takes place, and we are getting the more selective, but sometime we are getting as a mixture alpha beta mixture of that glycosides, because we are talking about O glycosides means oxygen atom are involved when the bond is formed between two monosaccharide units, because we are talking again about the that disaccharide, or we can call it as a oligosaccharide. In the oligosaccharide, as we know that in the while studying as a classification, we have learned oligosaccharide further divided into three types. One is a disaccharide, trisaccharide, and the what we can call it tetrasaccharide. These are the sub type of that oligosaccharide. So in that we are talking some of that oligosaccharides. So here is some example for gal B, gal B, gal N and L ribonose, gal C are shown in a scheme number 2. Yesterday we have seen that scheme number 2, how they form as that gal, that what we can call it as gal B or gal and gal N, then rhino alpha. So that type of the scheme number 2 we have studied with the very essentially what are the point to remember, or what are how to write those structures, how the reaction carried out, what are the selective reagent, and what is the temperature, reaction condition, all these essential, how that process is designed. So that type of the discussion we have discussed yesterday. So today we are discussing remaining scheme, that is the scheme number 3 and scheme number probably we are going to discuss right now. And before, and in general, glycosylation yields are high, as we know that. And yesterday's scheme number 2, if you observe carefully, what will you notice over there? You will notice there all the yield are more than 75%. In one scheme you will find 75%, another one is 90%, 93% and 96. So the whatever resulting product in those reactions, these are high yielding product we are getting, and that the speciality of this reaction, and therefore we are discussing this one. In general, glycosidic yields are high irrespective of the anomeric configuration of the trichloroacetamide, and only one anomer is obtained. Only one. Selective is very essential, because if in organic chemistry, remember, the single step and the product is what we can call it as a selective product, specific product. If there is a mixture of products are obtained, then it is very difficult to separate those products. If you separate it, then there is a loss in the yield, and once the loss in the yield, then there is a question arises or comes about the cost of that designing that process. So everything is there. So the purity of that compound, and for isolation or for purification we have to use different technique, and by using this different technique, the cost of that process is goes on increasing, and therefore the selectivity while carrying out, while getting this product are very high, and that's why the single product there is no need of that what we can call it as a separation. So we can carry out we can achieve the purest form of the compound with greatest selectivity, means stereoselective, regioselective, chemoselective, that type of the word generally we are hearing in the organic chemistry. So that type of the things are here, and we are getting only single product with the highest purity, with the high yielding product these are, and therefore it is a very important as well as research point of view is concerned. Occasionally when glycosylyl acceptor with more than one free OH group are used, high regioselectivity is obtained because of the different reactivity of the OH group, because there are the number of different hydroxyl groups are present in that monosaccharide unit, and therefore different hydroxy group has their different reactivity, different selectivity, and different reactivity are there, and therefore selectively we can choose the reaction, we can carry out the reaction, and we will get so one may play the role as a donor, and another monosaccharide unit can be act as a acceptor, and when these two things combined together, the resulting compound is obtained with the greatest selectivity. That is a main theme of this carbohydrate chemistry, and it was found that dichloroacetamidates donor are especially appropriate for deactivated, that is a fluorine containing donor, in contrast to other glycosylyl donors, thioglycosides, etc. When we introduce at anomeric carbon atom by that trichloroacetamidates, then that reactivity of that anomeric hydroxyl group is decreased, or what we can call it deactivated, but now it becomes as a donor now, and then that hydroxyl group is a donor, but in the other way round, in other monosaccharide unit, that hydroxyl group now becomes as a what we can call it as a acceptor, and therefore there is a attraction, electrostatic force of attraction is generated. One is the donor, one is the acceptor, and reaction takes place and the products are formed. So that is a general concept over here. A highly convergent synthetic method has been developed for the synthesis of cellulose and other oligosaccharides via di and tetrasaccharides, which can be converted either into glycosyl donors by dealkylation and transformation into the trichloroacetamide, or into acceptor by deacetylation. That is the scheme number, say third is shown over here. Let us see what is that scheme number 3. I am going to represent here, that is a scheme number 3 over here. And now here in this case, let us begin from here. So I must draw this structure over here. This is a shear form of that glucopyranose type of the compound, and generally here this will be OAC, this bond get here acetylation OAC, then OAC, I am writing this one, and now here O all, and here we can write, here is a O-pioinyl, pioinyl. So that all these are the what we can call it. This is a compound that is a glycoside, and now this further treated with some reagent. Reagent number 1 is used as a ACO2, selenium dioxide, in presence of acetic acid, ACOH, and second reagent used here is a what is that, CS3, that is trichloroacetamide, CCN, in presence of DBU. So that is a DBU. These are the reagent used, and after using these reagent here, what do you get? The product we are going to get here. Here these are pivinyl, and here acetyl on those side. And now remember, make the correction over here. After treating these reagent or these substrate, the product formed is like this. Look at here. Here I am showing that structure like this. So what is going to happen? This remains as it is. Here this now. Here this is going to convert into the O, then double bond NH CCl3, that is a trichloroacetamide type of the compound is formed over there. Other part remains as it is, pioinyl, then here OAC, and here also they are present at equatorial position, and here PIV. So pioinyl compound, it remains as it is. So this is the thing we are going to get over. What this compound O hydroxy group, they are acquired at equatorial position, and that is known as a trichloroacetaminates, and trichloroacetamate that becomes as an donor over here, and now disaccharide immediate, and now here DBU and methanol. Now here is a DBU in presence of methanol, as we know that MEOH. The resulting compound obtained will be here only what we can call it as a neighboring group participation occur over there, and this acetyl group get converted into one specific selectively at that position. Now remember this other thing remains as it is O all, and here O PIV, and here also O PIV, and here also OAC remains as only changes. So at this position that becomes as a hydroxyl group OH. So that is the thing is happening over there here. And now when these two combine together, this and this combine together, and the in presence of trifluoro OET twice, trifluoroetherate. This is known as a trifluoroetherate. After that, these two separate set compound bring together and treat with that BF3OET3. The name of this reagent is a trifluoroboron etherate. So that is generally what is used there, and what you are going to get over here. Now this part and this is going to react together. How the reaction takes place, because it is a donor and now it becomes as an acceptor, and how they come together. Here I am writing this one is as it is over here. Now I am showing here this is a structure. Now this O stereoselective comes above, and now and then this hydroxy group, and for that this hydroxy group when comes here, we can write the structure is like this. So this is a structure. Now one is like this, another one I am flipping like this, so exactly opposite, so that we can show this hydroxyl group how it comes over there. Here is a here make the correction over here, BN benzyl compound. Here is a OBN. Here also what is going to happen now there, when these two combine together, OBN benzyl compound over there, only acetyl get it remains as it is. But here if you do this reagent DBU in presence of methanol, this acetyl group neighboring group participation, so it convert into as a hydroxyl group, and that becomes as a acceptor, and this with this suitable reagent selenium dioxide in presence of acetic acid and the trichloroacetonitrile in presence of DBU, that gives this type of only here the changes are occur at anomeric position only, and then when these two are bringing together in presence of trifluoroborane etherate, it gives. So other part on this side, if you observe this structure carefully, you can able to draw as it is OPIV, then here OAC acetyl group, and here at equatorial O benzyl group as it is, and then now this side, right, this side is now we can write below. So how do we write? Here is a OBN, and now here this one should be OPIV, because here downward OBN comes here above, then here remains as a OPIV, and here at equatorial position that O. So this is the what we got here. We got here as a dry, what we can call it as a disaccharide type of the compound, disaccharide compound we got over here. So that is a highly stereospecific or stereoselective compound. Now these two further we can write over here. So this again is going to, this is a disaccharide immediate, this is a disaccharide immediate, again disaccharide immediate, and here will be the disaccharide acceptor. Here the disaccharide acceptor, acceptor with this disaccharide immediate and the disaccharide acceptor, when they bring together here and in presence of again trifluoroethylate BF3OET twice, that is a boron etherate. So that when you treat with, what is going to happen, this type of the two molecule get combined together over here, and the resulting compound formed will be like this. Let me show that one here. So let me clean this one so that we can easily draw that structure over here. So after that we are going to get over here the structure are like this. So here we can draw the structure, one structure over here, then O, then this should be like this, the structure, and then another structure will be here like this, and that again becomes this one, and after that we can draw this structure once again here, this one, this is a structure. So these two structure combined together, and we are going to get here, we are talking about, so other part, so this part, as we know that it remains as it is here, and at this position what is, there is OPI, this one remains as OPIV. So this part, this molecule we can write as it is here OPIV, then here OAC acetyl group, here O benzyl group, and here OPIV, that remains as it. Now look at this carefully. What are the what is there here? OBN, then at this position OPIV pioneal, and at this position there again OPIV, that's it. And then moving toward as a this one once again, that is a that becomes exactly similar to this one. Now here OPIV, then equatorial position OBN, here OPIV, this form there, and now this is similar to this one. So OBN, then here OPIV, and the terminal position. Now this one OPIV and here O. So this is a compound which we are getting over here. From this we can get this one selectively. So now what is going to happen? Next one also is a so similar one. So here what you are going to get, and here again from this you are going to get is a tetrasaccharide immediate. It is a tetrasaccharide immediates, and from this we also get tetrasaccharide acceptor. Here tetrasaccharide acceptor, right? When this tetrasaccharide immediate as a donor and tetrasaccharide one is an acceptor, when they come together like this is going to come together in presence of what? That is a BF3 etherate. It was in presence CH2Cl2, that is a dichloromethane at 0 degree centigrade. 0 degree centigrade as a temperature is kept over there, and what you are going to get over here, there the molecule you are going to get over here. So this molecule is like this. Once again you can draw for this one as it is, then oxygen atom, then you can draw this structure, this oxygen atom, and now this one, this, then you can draw this oxygen atom, then here oxygen, then this one, so you can draw this one. Here is a 4, and now here once again 1 2 3 4, and once again there will be this one, then this, and what do you get? You are going to get over here this one. This is a structure which we are going to get over here, C, and then here once again, then there will be, you can draw like this. So 1 2 3 4, right? And again once again this one, no, this one is a something else from this. So let us see here. 1 2 3 4, 1 2 3 4, they are as it is. Now then 1 2 3 4 as it is, then above one this becomes above 1 2 3 4. Yes, let me draw properly here. Once this one, once again this you can remember this one, and now here is oxygen, then you can draw this structure once as it is O, this one, and now oxygen, this one, then you can draw this structure, oxygen atom, this structure you can draw as it is here, oxygen, this one, once again O, then this one, this is the structure you are going to get. Then O are all these 1 2 3 4 5 6 7 and 8. This is the biggest structure, but think you have to combine this. So what we did, first we have taken on both sides, and then now here whatever things are there, you can write down as it is O P I, not this, not like this. This is O P I V, then O A C, and here once again O B N as it is. Now here is O P I V, you can write as it is. Then here O B N, and this side once again O P I V, here O P I V. Then here the third one, you can write O P I V. Here equatorial position BNO, here again O P I V. At this position again, once again OBN, you can write as it is, and here OPIV, and here once you can write OPIV, and that is there. And now come, these are the fourth one. Now here at this position once again there is OPIV, and here you can write OBN, and here as it is OPIV, and here you can write this one OPIV, here you can write OBN, and here OPIV, PIV, that's it. And here once again, here you can write OBN, here is OPIV, and here you can write as it is OPIV, Pavanil. And look at the last one OBN as it is, and here this one OPIV, and this one is a OPIV. That is a scheme. This is a scheme number 3. Just now we have discussed. It looks as a big, but once you remember the pattern, how to attach those groups, starting from that we can easily, because we are talking about the trichloroacetamide. So this is a scheme number 3 which we have seen over here. Now the use of paramethoxybenzyl groups PMB instead of acetyl groups was less successful. The combination of acetyl pivolyl and benzyl groups leads to the proper balance between stability and the reactivity of trichloroacetamide as a donor and the acceptor substrates. High yields were achieved by using a specially developed high vacuum system for glycosylation under anhydrous condition, and therefore this is a very high yield process and selectivity is very good here in this case, and that's why it has a prominent benefit in the field of carbohydrate chemistry. So I think we have discussed today one scheme, that is a under the trichloroacetamide, how it works and how it can be proceed smoothly, and how to remember, how to draw this even though complicated structure in a very systematic way. That's the main point we have discussed today, scheme number 3. So tomorrow we will discuss the remaining, that is a scheme number 4th onward, and how, because we are discussing about the formation of glycosidic bond, or the glycosidic linkage, or the synthesis of oligosaccharide. Oligosaccharide, generally this is belonging to the O glycosides. So that's the thing we have discussed today. So remaining we will see the next lecture. Thank you. Have a nice day.